All right, guys, so today we are going over chapter 5.23. We are finishing up chapter 5.2 today. And what we're doing is adding, subtracting, simplifying radicals. Now, the first one we have is this one here, the fourth root of 10 plus 7 times the fourth root of 10. Now, one way we can look at this and one way we can add these two together is by greatest common factor. Because both of these have the fourth root of 10 in common, we can factor it out of both terms. And if I factor the fourth root of 10 out of the fourth root of 10, we have 1. And if I factor it out of 7 times the fourth root of 10, what we would have left is 7 because we're removing that fourth root of 10 from both terms. And at this point here, we have the fourth root of 10 still. But 1 plus 7 is 8. Leaving us with the fourth root of 10 times 8, or really 8 times the fourth root of 10. And we can do this by greatest common factor, but we don't have to do it using greatest common factor.
Where do we get that?
If I remove the fourth root of 10 from the fourth root of 10, if I would factor it out of itself, it's 1. All right, guys, focus up here. All right, guys, focus up here. How many fourth roots of 10 do I have here? How many do I have here? 7. So if I add the two together, how many do I have? We have 8 fourth roots of. Well, here we are what? Adding. So I say that I had 2 times 8 to the 1/5, and I'm adding to it 10 times 8 to the 1/5. So total I should have we should have 12 times 8 to the 1/5. Because since those are the exact same, they are like terms, so we're able to add them together. Because if the radicals are the exact same, or what's inside the parentheses are the exact same, we can add them together. However, for the next one, the cube root of 54 minus the cube root of 2, we need to be able to subtract these from each other. But unfortunately, we cannot subtract them in their current form as they are, because those radicals are not the same. So, what we need to do is be able to simplify or rewrite the cube root of 54. Now, we can do this as we did the other day. We can look at the factors tree of 54, which is going to be, well, we can start with 2. 2 times 27. 27 is 3 times 9. 9 is 3 times 3, telling me the factored form of this is 2 times 3 to the third. Which means we have the cube root of 54. Well, not so much cube root of 54, we would want to replace it with 2 times 3 to the third minus the cube root of 2. At this point here, we would need to simplify. Well, the cube root of 2, we don't have enough 2's, so it's going to stay the cube root of 2. However, I do have enough 3's to take the cube root of it, because I need at least 3 of a factor to be able to pull it out, telling us that we have 3 times the cube root of 2 minus the cube root of 2. Since now they both have the same radical, we can subtract them. So I have 3 of them, and I'm taking 1 away, so I should have how many? 2 cubed roots of 2. And that's it. Questions on any of this here? Let's go and look at the next few. So the first one we have, number 10, 7 times the fifth root of 12 minus the fifth root of 12. Are the radicals the exact same? So really what we're looking at is what? 7 minus, and that would give us 6 fifth roots of 12. If we look at number 11, I have 9, 4 times 9 to the 2/3 plus 8 times 9 to the 2/3. These two are the same, yes? So that means they are like terms, so we just need to add what? 4 and 8, giving us 12 times 9 to the 2/3. Because those terms are the same, we can just add those numbers together. Questions on any of this here? Cube root of 5 plus the cube root of 40. Are these radicals the same? No. But if we're going to be able to add them, realistically, I need it so I have the cube root of 5, because that's as simplified as it gets, plus most likely something times the cube root of 5. I need both of those to have the cube root of 5, yes? Because that's the only way we can add or subtract is if those radicals are the exact same. So what that's telling me is I need to rewrite the cube root of 40 as something times the cube root of 5. There should be some perfect cube, some perfect int power that we can factor out. And one of the factors that's going to have to go with it is 5. What times 5 is 40? 8. So really what that's telling me is inside this here is that we have the cubed root of 8 times 5. I know I can't take the cubed root of 5, otherwise the other one wouldn't have it. So the main question is, can I take the cubed root of 8? Yes, it is 2. So it's telling me that the cubed root of 8 is going to come out as 2, cubed root of 5 stays. Now are the two radicals the same? Cube root of 5 plus 2 cube roots of 5 would be 3 cube roots of 5. We're using one of the radicals to figure out what we need to get the other one to be, so we can add or subtract, we can simplify, we can combine. Questions on these three here? Properties of rational exponents radicals can be applied here. Whenever we take an odd root of an odd power and those powers simplify, it's going to be what it is. Because if I take a positive number and put it to an odd power, 5 to the 7th power is this number here, and it's still positive. If we put a negative number to an odd power, it's going to stay negative. Odd powers, it doesn't matter what it is. I put a number to an odd power. If it was positive, it stays positive. If it was negative, it stays negative. And if I take the 7th root of 78,125, I get back to 5. If it had started out as negative 5, negative 78, it would still be negative 5. The sign doesn't change. We don't have sign issues. Now, 3 to the 4th power is 81. Negative 3 to the 4th power is still positive 81. So if we took the 4th root of 81, we would get back to positive 3, not negative 3. Because the 4th root of negative 3 to the 4th is going to be positive 3, not negative 3, because of how we apply properties of powers. So if we have an even root of a variable to an even power, we have to put absolute values around it to offset the negative. I'm not going to count off for it necessarily, but it is something to note. So with that in mind, let's look at simplifying these here. So the first one we have is the cubed root of 64y cubed. Well, the way we talked about it the other day, we can break it up into its two parts. The cubed root of 64 and the cubed root of y to the 6th. Cube root of 64, we could do the factor tree, break it down, and do that there, or I can let the calculator tell me what the cube root of 64 is, and it is 4. Now, because the calculator told me it's a nice decimal number, non-repeating, non-terminating decimal, we can just replace it. I don't have to do the factor tree with it. Now the question is about the cube root of y to the 6th. One of the ways we simplified these here was the nth root of a to the x is equal to a to the x over n. So for our y term, y we'd still have it as our a. In the fraction, the index, the root we're taking goes on bottom. The power connected to y goes on top. So the cubed root of y to the 6 is the same as y to the 6/3. What is 6 divided by 3? 2. So we're saying the cubed root of 64y to the 6 is 4y squared. So really, what did we end up doing? We just took that power and divided it by the index for these variables. Questions on this here for A? Since we took an odd root, we don't have to worry about sign issues. B, one of the ways we can do this is with our quotient property of radicals. We can split it to the 4th root of the top over the 4th root of the bottom, telling us that we have the 4th root of x to the 4th over the 4th root of y to the 8th power. Now, if we want to apply the same property we did with the first one, on top, fractional exponent, our index, what we're having the root of is going to go on bottom, so we're going to put the 4 on bottom, and we're going to put its power on top, which is also 4. So it's telling us that the numerator is x to the 4/4. We'll simplify that in a minute. The denominator, again, our root, our index of this radical is still 4, so it would go on bottom. The y's exponent this time is 8. So on top, 4/4 is 1, so we would just have x to the first, or just x. The denominator, 8 divided by 4 is 2. Telling us that we have x over y squared. Now, because we took an even root of an even power, we do have to put absolute values around the x because that variable cannot be negative. We cannot plug, we can plug a negative in for x, but we cannot have a negative come out because of the properties of roots and power. Now, we only put it around the top because the denominator doesn't make a whole lot of sense. Because the denominator is y squared. If y was negative, we're going to multiply it by itself, which is going to make it positive. So putting absolute values around a variable to an even power is just redundant in what it's saying. But if you remember the absolute values or don't, that's fine. We still get to the same thing. X over y squared. Questions on either one of these here? Well, as I said a minute ago, really what we did here and what we did here is we were just dividing the index by the exponent, yes? So here, 4 divided by 4 is what? 4 divided by 4? 1. So it'd be x to the first. 8 divided by 4 is? Same thing. Same property, we just didn't write it out. Cubed root of 27d to the 12th. Two main parts that we have. We're taking the cubed root of 27 and d to the 12th. Well, if we wanted to, since 27 is just a number, I can see if the calculator will tell me what the cube root of 27 is. Lo and behold, it is 3. Now d to the 12th. Now we could rewrite it as d to the 12 thirds, but really what are we doing? We're dividing that exponent by the root. We're saying how many times or how many groups of 3 d's can I take out of 12? Well, what is 12 divided by 3? 4. So the cube root of 27d to the 12th is 3d to the 4th. Questions on this here? Questions on A? D, same thing as we did before. We could break it up into the 4th root of x to the 4th over the 4th root of y to the 16th. But really, we're just dividing the exponent by the root, the exponent by that index. X to the 4th. If we take the 4th root of it, the 4th root of x to the 4th would be x. 4th root of y to the 16th, 16 divided by 4 is 4. And really, we would indeed put the absolute values around the x because it's to an odd power. Really, if we take an even root of something and end up with an odd exponent, we need to put the absolute values. If we end up with an even power, we don't need them. Questions on those here? Now, another way to get around putting those absolute values is just to assume all variables are positive. We don't even have to think about it anymore because we are not going to put a negative value into these variables because we just said they're going to be positive. And what we're going to simplify now is this here, the 5th root of 4a to the 8th, d to the 14th, c to the 5th. And for these here, it might be helpful for us to think of it as the 5th root of each of its parts. Now, out of these 4 here, 2 of them are going to be nicer than the other 2. So the first one I'm going to look at is the 5th root of 4. Now, at this point here, we should know that the prime factorization or the factored form of 4 is 2 squared. So what we're looking at is the 5th root of 2 squared. Now, if I had 5 factors of 2, it and the 5th root would simplify out. But let's think back to our simplifying rules. I'm going to go in reverse order. Number 3 says we cannot have a radical in the bottom of a fraction. Here, we do not have a fraction, so that doesn't matter. Our second one said that we cannot have a fraction inside of a radical. Again, doesn't matter because we have 2 squared. We don't have a fraction. And the last one says we cannot have perfect nth roots or perfect nth power inside of a radical. 2 squared doesn't simplify. I don't have enough 2's for it to simplify with that radical. So is there anything we can do with the 5th root of 2 squared? No, there's not enough to do with it. So we don't do anything to it because we can't reduce. We're just trying to simplify perfect nth roots out. So let's look at the 5th root of a to the 8th. When we're simplifying this here with variables, one key giveaway that we have to reduce it is if the variable's exponent is bigger than the root. Here the exponent's 8, the root is 5. That means something's going to reduce out. We're going to simplify out. For it to reduce out, we need groups of 5. We need it equal to the index. Yes? Well, with 8, I do indeed have one group of 5 A's, yes? But how many more A's are being multiplied together? Because we have 5 of them. Then do I have another set of 5? Now, how many more do I have? 3, because they have a total of 8. Because when we multiply like bases, we add those exponents. So a to the 5th times a to the 3rd would indeed be a to the 8th. Questions on this here? How many groups of 5a's can we take out? 1 because we only have one a to the 5th. So it would come outside. But the a to the 3rd would have to stay inside because we do not have enough a terms. Questions on a before we move to b? 5th root of b to the 14th. How many groups of 5 b's, or how many times can we divide 5 into 14 evenly? 2. Because b to the 5th times b to the 5th, that'd be to the 10th, yes? How many extras do we have? 4. So that tells me I can simplify 2 out. I can pull out b squared, but I'm left with 4 inside. I can pull 2 full groups of b out, but I have 4 left over inside. And lastly, we have our c. This one's nice. What is the 5th root of c to the 5th? C. Simplifies once. Questions on this here? Let's write our answer. So we're going to write the finalized answer. Let's see what came out of the radical. With our number, nothing came out. But with a's, we have a single a that came out of the radical. B's, we had 2, so we had b squared. And c, we just had 1. So ab squared c is what came out of the radicals. But we still had a few things left inside. With our first one, our number 2 squared was left inside, but we don't want to leave it as 2 squared. 2 squared is what? 4, so we'll leave the 4 inside. With our a's, we had 3 of them, so a cubed. B, we had 4. C, we didn't have anything. So our final answer is ab squared c times the 5th root of 4a cubed b to the 4th. That's it. We pull everything out that we can. What we can't gets left inside. Questions on this here? Questions on this so far? Okay. You need to find this problem here. If it's not the next one, it's probably 2 after it. We were able to find this. Okay. I've been meaning to rearrange this note sheets, and I did it this morning, so those are not up to date. Now, just like the last one, we're going to break this into its parts. And luckily enough, they were nice with at least 2 of them. And one of them is the cubed root of 2. 2 is prime. Can't take the cubed root of it, can't reduce it without turning it into an irrational number. Cubed root of a to the 13th. How many times can I divide 3 into 13? 3. So we have 1, so that's 3, 6, 9. Can we keep going? 3, 6, 9, 12. So we can actually do it 4 times. So 3 is not wrong. We can just do it one more time, which tells me I can take how many a's out of the cubed root of a to the 13th? 4, because it can go into it 3 times. 3 can go into 13 4 full times completely. We can take 4 groups of 3 a's out, telling me I have a to the 4th over or with the cubed root of a to the 1st, because there's 1 left over. Questions on a before we look at b? What is the cubed root of b to the 3rd? B. That's nice. And last one, the cubed root of c to the 8th. Yes, because we can do c cubed times c cubed, because that's 3/6. We need 2 more to make 8. So we can divide, or we can remove 2 groups of 3c's out, but that leaves us with 2 inside. So our 3 terms that got removed from the radical was a to the 4th, b to the 1st, c squared. And what got left inside the cubed root was 2a c squared. Questions on this here? So a lot of this is just reducing the radical, seeing how many groups of that index we can remove, and going from there. We could have divided it and see how many of the whole part comes out. Fractional part stays in, but we can't leave it as fraction. We have to see how many of that group. We ready for the next one? Need you to find x squared over the cubed root of y to the 13th. Should probably be close to the one we just did. Now, the issue with this one here is that we cannot have a radical in the bottom of a fraction. We've done these already. We just multiplied it to get to the index of 3, and we were good there. However, 13 is already bigger than our index of 3. Now we're still going to have to multiply the top and bottom by something to get that radical on bottom to simplify. And it's going to be y, because we're going to need a y term. Because really we want that root and the power to simplify out. We need it to divide out, just like we did on the last one. Because if I try to simplify this here, 13 divided by 3 does not divide nicely. What is the next number after 13 that divides by 3? Well, what's the next number after 13? 14. Does it divide by 3? No. So then we can try what? So the next power after 13 that's divisible by 3 that would simplify that root is 15. How far are we away from 15? 2, because we're going from 13 to 15, so we're 2. Which tells me I need how many more y terms? 2. So what we're going to do is multiply the top and bottom of this fraction by the cubed root of y squared. We're multiplying it by how many more terms we need to get to the next power that would be divisible by the root. So since we're doing roots of 3, cubed roots, we're looking for the next number that's divisible by 3. If it had been fifth roots, we're looking for the next number divisible by 5, or whatever that root is. Because if we multiply this here, we would have a cubed root. Y to the 13 times y squared. When we multiply like bases, we add those exponents. 13 plus 2 is 15. Cubed root of y to the 15th, we can divide that exponent by the root. 15 divided by 3 is 5. Yes. But we also have to multiply the numerator, our x squared, and the cubed root of y squared. Since the x squared does not have a radical, we cannot multiply what's inside. It just tells me it's x squared times the cubed root of y squared. Questions on this here? Questions on any of this so far? All right, you're going to have to turn backwards because we want to find x over the cubed root of y to the 8th. Were y'all able to find this one here? So again, the issue with this here is that we have a radical in the bottom of a fraction. Now, for whatever reason, both of them decided to be cubed roots, but that's fine. Because again, when we simplify radicals, as I've seen and kind of pointed out, we're really dividing that exponent by the root. So if I wanted to divide out, I really need to have an exponent attached to y that's divisible by 3, because that's our index, yes? What's the next number after 8 that divides by 3? Because we always want to go up. Because we know it's not 8. So what's our next number? Is 9 divisible by 3? So that means we just need how many more? 1. Because the cubed root of y to the 8th times the cubed root of y, 8 plus 1 is 9. And the cubed root of y to the 9th, 9 divided by 3 would give us 3. Hint, reminder, something to know, whatever we multiply this by, the exponent attached to the variable inside that radical cannot be bigger than the index. I would not multiply this by y to the 3rd, the cubed root of y to the 3rd, or cubed root of y to the 4th, because we're trying to get it to simplify. Anything we go above that is going to give us extra factors that have to simplify out. But we also have to multiply the top. Since x does not have a cubed root, we can't multiply the x and y together. The y inside the cubed root and the y on bottom cannot simplify because the one on bottom does not have a cubed root anymore. So it's just x cubed roots of y. Questions on this? Here. 14xy to the 1/3 divided by or over 2x to the 3/4 z to the negative 6. We want to simplify this as far as possible. Now, part of the reason we can't leave it as this here is, well, 14 over 2 are like terms. 14 divided by 2 is 7. Next thing we have is we have x on top and bottom. We cannot leave like bases being divided. When we divide like bases, we subtract the exponents. So x over x to the 3/4, according to our division property, would be x to the 1 minus 3/4, numerator divided by the denominator. We'll simplify that here in a minute. The next variable we have on top is y. There is no y term on bottom, so we leave our y to the 1/3 on top. If the y to the 1/3 had been on bottom, we would have left it on bottom. Now the only other variable we have is z to the negative 6th. We cannot leave that exponent negative. We have to make it positive. And to make an exponent positive, we've got to move it from the bottom of the fraction to the top, or top to the bottom. Now the only thing we have left to do is just simplify our 1 minus 3/4. At this point here, we can grab a calculator and say 1 minus 3/4 is 1/4, telling us that we have 7x to the 1/4, y to the 1/3, z to the 6th. Questions on this here? All right. Mm-hmm. Let's look at this one here. 16xy to the 1/3 over 8x to the 2/3 z to the negative 4. So to simplify this, the first thing we need up here is those numbers are going to divide. 16 divided by 8. 16 over 8 is going to be 2 over 1, or just 2 in the numerator. Just like the one before, we do have x over x. X divided by x, when we divide like bases, we're going to subtract those exponents. We would do the same thing with y. However, y is only in the numerator, it's not in the denominator. So we just have y to the 1/3 in the numerator. Z to the negative 4, we've got to move it from the bottom of the fraction to the top to make that exponent positive. We cannot leave an exponent negative. And lastly, we need to just simplify 1 minus 2/3, which is 1/3. Tell me we have 2x to the 1/3, y to the 1/3, z to the 4th. And as that is it with that one there. Questions with this here? Okay. 4 more and we are done for today. A, 5 square roots of y plus 6 square roots of y. Are the radicals the exact same? Yeah, so we have 11 square roots of y. 5 plus 6 is 11, so we have 11 square roots of y. B, are the radicals the exact same? No. But for us to be able to add or subtract them, we know that these cubed roots need to be the exact same. Now the numbers outside, variables outside the radical, aren't going to simplify. They're not going to change. It's still going to have 12. We're still going to have z. Let's look at what's inside each one first. Inside the first cubed root, we have the cubed root of 2. There's no way I can take a cubed root of 2. It's as simplified as it gets. Which means that this other root, cubed root, should also have a 2. Because that's the only way we can subtract them, yes, if they both have 2's. Which is telling me I'm going to have to do something with 54. I also said earlier that if a variable has an exponent bigger than the root, it's going to need to simplify out. So on the one on the right, z squared, 2 is smaller than 3, so there's nothing we can do with it there. Which tells us what? The other one has to have a z squared. Z to the 5th, well, we can take one group of 3 z's out, yes? Which does match the other one with a z. Questions on this so far? So really the only thing we have left to fix is this cubed root of 54, yes? What times 2 is 54? Yes, 54 divided by 2 is 27. So what we're hoping is that I can take the cubed root of, telling me it is. So what we did there was just use both of them and looked at both of them and tried to get them both to be the same. Z times the cubed root of 2z squared, z times the cubed root of 2z squared. They are now both the 12 minus 3. 9. And then we have to put our z times the cubed root of 2z squared back. Telling us the final answer for this here is 9z cubed roots of 2z squared. Questions on this here? Are you ready for the next one? 6 cubed roots of x plus 2 cubed roots of x. 8 cubed roots of x. Last one. 16 times the 4th root of 3p to the 6 minus p times the 4th root of 48p squared. So we look at the first one. 16 is not going to do anything at this point. But inside that fourth root, we have the fourth root of 3. Can't take the fourth root of 3. P, how many groups of 4 P's can we take out of 6? 1. How many are left? 2. Wait a minute, we didn't even look at the other one, but is this here simplified as far as it gets? Yeah, which is telling me what? The other one has to be P. That 48 is going to have to change to a 3, and that other part is P squared. So really the only thing we're having to figure out is what the fourth root of 48 simplifies to, yes? Which should be a number times 3. 48 divided by 3 is what? 16. Fourth root of 16 is 2. Really telling me that the fourth root of 48 is 2 fourth roots of 3. 16 minus 2 is 14p fourth roots of 3p squared. And that's it. Homework's a worksheet. I will hand those out.